Since we have been talking a lot about energy, power, and the conservation of energy in the past couple of videos, I thought we should go over a quick problem that looks over how to apply everything that we've just learned. So this is a problem from the 2024 AP Physics 1 FRQ exam. So let's read the problem first. So a block of mass m, we're given that it has a mass m, is released from rest at point A, which is height 6r above the horizontal. And after being released, the block slides down the track. And released from point A, the block doesn't lose contact at any point. And points B and C are located at the highest points of their respective circular loops, both of radius r, and all frictional forces are negligible. Okay, if we look at the first question here, it is about energy bar charts. So diagram A is an energy bar chart representing the gravitational potential energy in block Earth system and the kinetic energy of the block at point A. So I'm just going to label this as point A, okay? And now we're going to draw the energy bar chart in diagram B that represents the gravitational potential energy and kinetic energy of a block Earth system at point B. So let's again go label that point B just so we are more clear about that. So if we look back at point B, we know that point B is a height 2r above the ground, right? Because we have two radii, so its diameter would be 2r. So as it says here, B is a height 2r above the horizontal. So let's think about this. Here we're given that initially at height A, it was 6r above the ground. So that makes sense. We have around 6 ticks over here. That would be equivalent to 6r. So now that we know that point B is a height 2r above the ground, we can simply use the same scale and draw the potential energy diagram here as a height 2r above the ground. So initially it has potential energy mg times 6r, but now it has potential energy mg times 2r, and the ticks perfectly represent that. So now, since we know that energy is conserved, there's no work being done on the object in this block Earth system, we know that the initial energy must be equal to the final energy over here. And the initial energy is just mg times 6r. So if we have mg 6r must equal mg times 2r plus the kinetic energy at point B. So that means the kinetic energy at point B must be mg times 4r, right? And even without calculating that, we know that initially it had 6 ticks in the first graph. So we know that it must also add up to 6 ticks in the second graph. So since we've already used up 2 ticks, we know that the kinetic energy must only use up 4 ticks. So that's how we get the potential and kinetic energy diagrams. Now we can move on to the second question. So part B asks us to derive an expression for the speed of the block at point B and express our answer in terms of r and physical constants. So physical constants in this case just refers to like gravity, for example. Okay. So let us write the fundamental physics principle for our derivation. So we know that the energy must be conserved. We know that E initial must equal E final, since there's no work being done on the block in this system. So we know from our last problem that E initial was equal to mg times 6r. And this is the total mechanical energy, Okay, so if we have mg times 6r, and we're asked to find the speed at point B, we know that from the last problem, the potential energy is mg times 2r, and the remaining is just kinetic energy, right? So we know that the kinetic energy is equal to mg times 4r. And kinetic energy can just be written as 1/2 mv squared. And we're going to set that to mg/r again. And if we cancel some things out, we see that the velocity squared is just equal to hgr. And that means that the velocity is the square root of hgr. And we have our answer right there. Okay, so for our last question, we have two parts to this last question. The first part tells us to draw and label the forces that are exerted on the block as the block slides through point C. So if you remember, point C was kind of like a circle like this. So it was already 2r above the ground, and it also had a radius r. So that means that the height of point C, if we take the ground to be height equals 0, the height of point C is equal to 4r, right? Okay, so that isn't very relevant to this part, but in the next part we'll see why that is relevant. So if the block is at point C, then what forces are pointing on it? So let's think about that. So obviously we're going to have the force of gravity, right? Label the force of gravity. That's always pointing down toward the center of the circle because it's pointing down. Gravity's pointing down. We know that. So what else is acting? So if we think about it, we know that it's traveling on some sort of segment of the curve right here. So the segment of the curve must be pushing down on the block as it's traveling. So we have another force, the normal force. Now it doesn't really matter how long we draw this arrow because we're not really given much of context around that, so we can just draw them like so. Okay, so now we are on to our final problem. So this is about proving a statement wrong using what we know about the problem. So a student claims that 4r is the minimum height of point A such that the block can slide through point C without losing contact with the track after the block is released from rest. Briefly explain why this claim is incorrect. Okay, so as I just mentioned, height C is 4r. If we set height A to 4r, then the gravitational potential energy at point A is equal to mg times 4r. And it has no kinetic energy at point A, so that tells us that the entire mechanical energy is just mg/r. Now, why does that give us a problem? You might be thinking, well, if it has enough energy at point A, then it can reach point C because point C will also have a potential energy of mg/r. Now, the problem is that if they were both equal, then it would also have zero kinetic energy at point C. And this is a problem because if it has no kinetic energy, then it's just going to fall straight down, meaning that it will lose contact with the track at point C. If this question were different, if it were asking, what is the minimum energy or what is the minimum height at point A such that the block will just reach point C, then it would be 4r. But this question is asking, what is the minimum height at point A at which the block will travel through the entire track without losing contact? So if it's without losing contact from the track, then the height will have to be greater. The height will have to be greater than 4r at point A so that it doesn't lose contact and fall down at point C. So I hope that has made a little bit of sense to show how energy can be applied to problems and also helped a little bit with your AP Physics if you just so happen to be taking it. I hope you guys have enjoyed this video and learned something new. Stay tuned for more videos.